This program is brought to you by Emory University.
Ice happens to be one of the most sensitive indicators of climate change. The amount of ice coverage on the polar regions of the planet is highly susceptible to temperature fluctuations and changes in the ocean salinity and temperature. So if we can understand how fast ice is changing on our planet and what are the processes that are involved with this change, then maybe we can get a better handling on how fast our climate is changing. Okay, so Ilulissat, which means icebergs actually in the native tongue, is on the western coast of Greenland. And it's this large channelized region where a lot of the ice from the ice sheet up here on Greenland is flowing down into this one channel. And this part where the ice meets the ocean has been retreating many, many miles over just the last decade, which is alarming, but it's even more alarming if you look at how much it's retreated in the years before that. Glaciers have a tendency to advance and retreat all the time. This is a natural cycle of these tidewater glaciers. But I think what's happening here is that they're seeing that this particular retreat has a lot to do with the changing climate and a little bit less to do with natural varying cycles. What we do in the lab is try to understand all the forces involved in these glacial processes, things that are basically extremely difficult, if not impossible, to measure in the field. So we make model glacier experiments in the lab. We have icebergs that float in water, and we study the forces involved when they break apart and tip over and capsize. And with the goal of being, if we understand all the forces involved and what's going on, can we then think of better ways to monitor and understand how much ice is actually being lost from the polar regions of our planet. So those waves, you're like, oh, how impressive. But then, if you compare them to the size, suddenly that's a 20-meter wave. The amount of energy that's in one of these events can be up to tens to 100 kilotons of TNT, which is the equivalent of a few nuclear bombs. And the reason that this is quite important is because the frequency is a very robust thing to measure. We can compute what the frequency, if you will, the time period of this rocking motion based on the iceberg size. And this frequency will show up again in any earthquake signal, this exact same frequency. So if we can correlate the frequencies that they see in the earthquake signals with the frequencies of icebergs rocking back and forth in the water, then that'll tell you that's a direct measurement of the size of the icebergs that have broken off. The reason that I do what I do is because, we're supposed to, as a university researcher and as a scientist, we're supposed to be thinking about some of the biggest problems facing our planet and facing humanity. And I feel like with the experiments we're doing here, we're making a contribution to understanding how to best monitor and predict what's going to happen to our planet in the future. And I'd like to think that a few decades from now that we were able to do something.
The preceding program is copyrighted by Emory University.